Hi, this is Kevin at the Virtual Planetarium at Raritan Valley Community College. Welcome to our weekly Star Talk. Today we're going to be giving you an update on the James Webb Space Telescope. But before we do that, let's talk about our upcoming moon phases. We have a new moon on February 1st, we have a first quarter moon on February 8th, and then we have a full moon on February 16th. Okay, so today we're going to be talking about the James Webb Space Telescope, which is what we have right here. As a recap, the telescope launched on December 25th of last year, and it was heading to a special point in space called L2, which is the special orbit just past the orbit of the Earth over here, but it's still going to be moving around the sun with the Earth, so we'll still have be able to communicate with it very easily from here on Earth. Well, the big news is that it finally made it to this point. It's officially inserted into its orbit around the L2 point. If you missed our last video, I'm going to put a link for that video in the description for this one so you can see the type of weird orbit it's going to be taking around our sun, but it's still very interesting. So again, it finally made it to the special point orbiting this L2 point in space, and all of the incredibly complex parts of the telescope have successfully been deployed. As a reminder, the telescope flew up into space, fit into the top of a space shuttle just like this, and it was very folded up. It was like crammed right into here. The mirrors folded, the giant shield that it had at the bottom was folded. Everything was put away so it would fit it onto the top of the spaceship and fly it out into space. Well, it has finally completely been deployed, so now the telescope looks like this in outer space, and that means the giant sun shield that we see down here is completely unfolded. The telescope that was folded in half, we can actually see that right here. The sides of the mirror were actually folded backwards. That's completely unfolded. The secondary mirror, this part we have directly over my head right here, also unfolded. So we have all the parts of the telescope finally unfolded and ready to go. On top of all that, the main mirror, the primary mirror, is actually really complex too. It's actually really cool because it's made out of 18 individual mirror segments that together work as one giant mirror. So here we can see the primary mirror is this big thing right here, and then it's made up of 18 of these little hexagonal shaped sections. Each of these sections is actually its own mirror that can be independently controlled and therefore calibrated. So when they're aligned perfectly well, they work as one giant mirror. Now, each of these has been tested already and they're deployed, so we're able to calibrate them as soon as we turn on the telescope itself. So that's going to be the next step in the mission. Alright, so if that's what's missing, what are we waiting for to actually turn on the telescope and calibrate it and get it ready to go? Well, the telescope actually has to cool down a lot more. Here we have in this other cool webpage, I'm going to put the link for this in the description as well, we have the current temperature of the telescope, we have the cold side of the telescope, which is the side that is protected by this shield. It is currently at minus 348 degrees Fahrenheit. Well, the working temperature of the telescope is actually about 370 degrees below zero. So it still has a long way to go until it cools down, and it's actually just losing heat passively, so it's literally just a waiting game until we wait for that heat to dissipate, for the telescope to reach its operating temperature, and then we can actually turn it on, test out the instruments, calibrate it, and then start looking at things in deep space. Now you might be wondering, why exactly does it have to be so cold again? Well, Webb will be looking out into space, but instead of looking in visible light, which is the light that we can see with our eyes, it's going to be looking in infrared light. Infrared is better understood as heat, and since this telescope is going to be looking so far away at very, very dim objects that give off very, very dim heat signatures, we need it to be as cold as possible so the instruments can pick up these very, very faint signals from far away in the early universe. Now, it's a pretty hard concept to understand why infrared lets us see further and why it's really heat, so I have a few examples for you all. Now, here we have the first example I'm going to give you is a picture of something called the Pillars of Creation. These are giant gas structures in the Eagle Nebula, and they're called the Pillars of Creation because these giant pillars of dust that are in outer space are actually creating new stars, so hence the term Pillars of Creation. It's a fun name. Now, this is what the pillars of creation looks like in visible light. So this is what the Hubble Space Telescope saw when it looked in the visible wavelengths, in wavelengths that we can see with our eyes. And we can see that there's a bunch of stars in the background, but we have these giant pillars of dust that don't really let us see any further than that. However, if we were to look at this in infrared light, so we can actually shift this over, I'm going to put the link for this website in the description as well. It's actually a really cool website where we can see a lot of these examples. So if we shift this to infrared, we can see a lot more stars, and we can see basically through these giant gas and dust pillars in space. And that's because that's what infrared lets us do. So when the stars are behind these giant plumes of gas, or nebulas, we can't see them in visible light. But these stars are actually heating up the gas ever so slightly, and when we look at them through infrared light, we can see where this gas is glowing, where it's a little bit warmer, and that's how we can see the imprints of the stars in the gas, revealing what's behind this nebula. Now, another example we have is using infrared to see really, really far galaxies. The reason this works is because the dust in these galaxies really far away. So for example, right now we're seeing these in invisible light, and we can see these two nearby galaxies that are just bright and visible light. But as we go to infrared, we can start seeing other galaxies further beyond these close galaxies being revealed, because the gas in these galaxies is also being heated up by the stars in the galaxies. So that stands out a lot more in infrared light, since there really isn't much else around it in terms of hot gas and stuff like that. So that's how infrared lets us see a lot further and lets us see galaxies that are from the early universe as well. Now, there's also a whole YouTube page courtesy of the Space Telescope Science Institute on YouTube, and they have a bunch of videos showing different deep space objects in visible light versus infrared light, so we can see these comparisons a lot better. You're welcome to check this out as well. I'm going to put the link for this in the description as well, so you can play with them a little more if you'd like. And we can see the same thing happening over and over again. We can see more stars past the nebulas that we can't see in visible light, but we can see in infrared light. A lot of these objects in this playlist right here are deep sky objects, but they're fairly close to us. They're not that far away. Well, James Webb Space Telescope is going to be seeing things much, much further away because it is a much bigger telescope. It's going to be a very big telescope. It's a very sensitive telescope, so we're going to be able to see these heat signals really, really far away. And to be able to see these signals, since they're so dim, we need to have the telescope really, really cold. So that's what we're waiting for, basically. And then once it reaches that temperature of negative 370 degrees Fahrenheit, we'll finally be able to start calibrating the mirrors, moving them so they're aligned perfectly, and then we're going to be able to start seeing all these different treasures in deep, deep outer space revealed by this magnificent piece of technology. Thank you so much for joining us. Hope you learned something new. Again, I'm going to put the link for all those videos and all those resources in the description of this video so you can check that out. It's really fun to just play with it and see how things look in different wavelengths, so you should definitely check that out. If you like this video, be sure to give us a like, and if you haven't yet, please subscribe to our channel. We're going to be putting out a new video every week. Once again, thanks for joining us, and hope you have a great week.